So, in the last lecture we were looking at momentum conservation and we had defined the stress tensor. Okay. Stress tensor sigma is equal to Ex So, this was the stress tensor. The first set of unit vectors, the left set of unit vectors in the left index is the direction of the force. The right set of unit vectors in the right index is the direction of the perpendicular to the surface at which the force is acting. Okay. So, at some point in the fluid, the force acting on a surface will depend on the orientation of the surface, but the components of the stress are independent of the orientation and they are single valued functions of position. So, this each component is a field. Okay. So, this tensor is called the tensor stress tensor field. Okay. And if I want to calculate the force exerted on a surface within the fluid, then that force is equal to the surface area into the stress tensor dotted with the outward unit normal to the surface. Okay. That is the definition of the stress of the force exerted at a surface, okay, in 3-dimensional space. Yeah. Okay. If I had some surface with outward unit normal n to that surface in 3-dimensional space, then the force exerted at that surface is equal to delta S, the surface area, times the stress dotted with n. Stress is a second order tensor, you dot it with a vector and gives you a vector, that is the force. Okay. Per unit area is the sigma dot n. I had shown you the last time that for angular momentum conservation, the stress has to be symmetric, that is the off diagonal terms all have to be equal. Okay. Okay. The off diagonal terms have to be equal from angular momentum balance condition. Okay. So, stress is a symmetric tensor, and in the absence of flow, the stress can be written as sigma is equal to minus p times I, okay, where the identity tensor is one okay, that is the identity tensor written without the unit vectors on the left and without the unit vectors on the right. Okay. If I include the unit vectors on the left and right, this will just be equal to Ex plus okay. So, this is a second order tensor. Okay. Here the direction of the unit normal is outward, whereas the pressure is compressive, and that is the reason that I have this negative sign over here. Okay. So, that is for the stress. So, in the absence of flow, there is a non-zero stress due to the pressure, okay, and that acts along the inward unit normal to any surface. It is an isotropic tensor which has the same magnitude in all directions in space. So, the magnitude of the pressure is a scalar whose magnitude is a constant at a particular location. The direction of the force is along the direction of the inward unit normal. Okay. So, what happens when there is a velocity field? Okay. When there is a velocity field, what is the expression for the stress? So, as you recall, the mass and momentum conservation equations related the flux to the gradient in the concentration field and the heat flux to the gradient in the temperature field. Okay. So, that was the relationship between the flux and the concentration gradient, the heat flux and the temperature gradient. So, you would expect the stress to be related to the gradient in the velocity, okay, because the velocity variations are what are resulting in stresses. Velocity variations cause relative deformation between nearby volume elements, and that is what results in a stress. Okay. However, the stress is a second order tensor and the velocity gradient is also a second order tensor. Okay. The velocity gradient is also a second order tensor. It will have 9 components. Okay. So, if I just write down the gradient of the velocity. The gradient of the velocity. Note that there is no dot product in this. Okay. There is no dot product between the gradient and the velocity. Okay. So, therefore, the dot product would be a divergence and that would give you a scalar. Whereas, this one there is no dot product. So, there are 2 directions here. One is the direction of variation, the direction in which there is a gradient. The second is the direction of velocity itself. Okay. So, if I expand this out, I will get E x partial by partial V x. Okay. Plus etcetera plus so, if I expand this out, it will have 9 terms because there are 3 terms in the gradient operator acting on 3 components of the velocity, resulting in a total of 9 terms. Okay. I can write this in matrix notation as E x, E y, E z into partial V x by partial x, partial V y by partial x, okay, partial V z by partial x, partial V x by partial y. You can verify quite easily that this matrix multiplication will give you back the expression that I had earlier. Okay. So, this is a second order tensor which has 2 directions. One is the direction of variation and the other is the direction of the velocity. Okay. One is the direction of variation and the other is the direction of velocity. And this tensor is usually written without the unit vectors to the left and the right. Okay. They are usually understood to be present whenever you write this gradient of the velocity. Okay. Okay. What does this mean? Okay. The gradient of any field is if you go a small distance delta x vector in some direction and take the difference in the value of that field at the location x plus delta x minus the value at x, okay, that is going to be equal to delta x dotted with the gradient of that. Okay. Same thing applied to a velocity. okay, in 3-dimensional space. Okay. If I am at a location x vector and I travel a small distance delta x to a new location x plus delta x. Okay. Okay. If the velocity at this location is v at x, okay, if I go to a nearby location, there will be a change in the velocity. I will get the velocity vector at x plus delta x. Okay. And the difference between the two vectors, the difference between the two velocity vectors is delta v. Okay. So, if I translate the velocity to the same point of origin, this is v at x plus delta x. Okay. The velocity at the location x is something like that. Okay. And the difference between these two, the difference between these two is delta v. Okay. The difference between these two is delta v. Okay. A vector, okay, the difference between the two vectors. Okay. And the relation for the gradient is that delta v is equal to delta x dotted with grad v. Okay. Okay, this is the relation for the change in velocity when you go a small distance delta x around the location x. Okay. And you can easily do this dot product. Okay. This will just be equal to, instead of Ex, Ey and Ez, I would just have delta x, delta y and delta z. Okay. So, I will get delta x into partial Vx by partial x Ex plus delta y into partial Vx by partial y, okay, Ex plus delta z into partial Vx by partial z Ex, okay, plus etc. Okay. So, that is the complete expression for the change in velocity when you go travel a small distance delta x vector, which has components delta x, delta y and delta z. Okay. So, the change in velocity in the x direction is the first line here. Okay. The change in velocity in the x direction is the first line here, because it has unit vector Ex. In the y direction is the second line, because it has unit vector Ey, and the change in velocity in the z direction is Ez. Okay. So, one can think about this as the change in the velocity of in one direction when you go a small distance in another direction around this point x. Okay. So, if I go a small distance in one particular direction around this point x, what is going to be the change in velocity in another particular coordinate direction. Okay. However, this also is a tensor. Okay. It has an identity which is independent of the coordinate system that is used to analyze it. Okay. So, this is also a tensor which has an identity that is independent of the coordinate system that is used to analyze this. Okay. So, as I said, the gradient of the velocity can be expressed okay, in tensor notation, in matrix notation, okay, partial V x by partial x. Okay, so this is one way of expressing it. This is a 3 by 3 matrix. A 3 by 3 matrix can always be written as the sum of, okay, a symmetric, okay, plus an antisymmetric matrix. Okay. You can always write a 3 by 3 matrix as the sum of a symmetric plus an antisymmetric matrix, where that symmetric matrix is equal to the matrix plus I should have plus its transpose times half, and the antisymmetric matrix is equal to half of the matrix minus its transpose. Okay. You can, where the transpose is defined by interchanging the row and column, okay, of the matrix. Okay. The transpose is defined by interchanging the row and column of the matrix. Okay. One can easily verify that if I take S plus A, I get back the gradient of the velocity matrix. So, this matrix S, okay, is basically the matrix plus its transpose. So, half of that. So, the elements of this are partial V x okay, then half of partial V x by partial y plus partial V y by partial x, half of okay, I just take this matrix, add the transpose, which is obtained by interchanging the rows and columns. Okay. Half of this is a symmetric matrix where the off diagonal terms are equal to its transpose. Okay. So, this is the symmetric matrix. The antisymmetric matrix is obtained by taking the matrix minus its transpose. Okay. So, let me just shift this here. Okay. The antisymmetric matrix has all diagonal elements as 0. This is be half of partial V y by partial x minus partial V x by partial y, half of partial v z by partial x minus partial v x by partial z. Okay. Half of partial v x by partial y minus partial v y by partial x 0 and 0. Okay, so this is the antisymmetric matrix. Okay. And you can easily see that these off diagonal terms are all the negative of each other. Okay. These off diagonal terms are the negative of each other, so that the transpose of the matrix is the negative of the matrix itself. Okay. So the antisymmetric matrix has only 3 independent components, okay, because the diagonals are 0 and the transpose of the matrix is equal to the negative of itself. Symmetric matrix has 6 components, 3 along the diagonals plus 3 others, okay, so that the transpose is equal to the matrix itself. Okay. So the rate of deformation tensor can be expressed as sum of a symmetric and an antisymmetric matrix. Okay. Now, for this symmetric matrix, you can see that the trace of S, okay, the trace of the matrix is the sum of the diagonal elements of the matrix. Okay. The trace of the matrix is the sum of the diagonal elements of the matrix. Okay. Partial Bx by partial x plus recall that this is the same as the divergence of the velocity. Okay. This is the same as the divergence of the velocity. Okay. Okay. Therefore, you can define an isotropic matrix, okay, as okay, as 1 by 3 times I times del dot V. Okay. Note that the divergence of V is a scalar. Okay. The divergence of a vector is a scalar. Okay. So, I can also write this as 1/3 del dot V, okay, into 1 0 0. Okay. 1/3 of the divergence of V into the identity matrix. You can see that the trace of this, okay, the trace of this, the sum of the diagonals is the same as the sum of the diagonals of the symmetric matrix. Okay. The sum of the diagonals of this is the same as the sum of the diagonals of the symmetric matrix. Okay. Therefore, I can define a matrix that has 0 trace by taking the difference between the two. Okay. The matrix with 0 trace, I will call it as the matrix E, okay, is equal to S minus 1 by 3 divergence of the velocity times I. Okay. So, this thing is an isotropic matrix. Okay. It has diagonal elements that are non-zero and equal, and the trace of this is just the divergence of the velocity. Okay. And therefore, the matrix E, if I write it out in long form, okay, in a manner similar to what I have done over here, okay, if I write down the expression for E in a manner similar to what I have done over here, okay, I will get this is equal to partial Vx by partial x minus 1 by 3 del dot V, okay, half of partial V x by partial y plus partial V y by partial x, half of okay. So, this is the matrix E, it is called extensional strain. Okay. And this matrix, as you can see, if you take the sum of the diagonal elements, you will get 0, okay, because the sum of the diagonal elements is partial V x by partial x plus partial V y by partial y plus partial V z by partial z minus the divergence of V, okay, that is equal to 0. So, this has 0 trace and it is symmetric. Okay. So, it is referred to as a symmetric traceless. Okay. So, therefore, the rate of deformation tensor I have separated out into an isotropic tensor here, okay, an isotropic matrix here, okay, that is 1 by 3 I into del dot V, okay, okay, which has equal terms on its diagonal plus something that is symmetric traceless, okay, symmetric matrix, the sum of the diagonals is equal to 0 plus an antisymmetric matrix. Okay. So, this is the decomposition of the rate of deformation tensor on the basis of its matrix properties. Okay. What kinds of deformation do each of these result in? Okay. What kinds of deformation? I told you that the velocity gradient tensor gives you the deformation, okay, the difference in velocities between nearby points. Okay. So, basically it tells you how a material element, okay, between these two nearby points will deform, okay, as time progresses, okay, because the left side of this material element is moving with velocity v of x, the right side is moving with velocity v of x plus delta x. Okay. Therefore, the change, any difference in velocity will result in deformation of this material element. Okay. And the nature of this deformation is contained in this rate of deformation matrix, which we have separated out into 3 components. What do each of these components physically represent? We will continue that in the next lecture. I will see you then.